Today we're going to look at vectors in 2 dimensions. Let's have a look at drawing the vector 4, 2. So the 4 at the top is telling us how far we are going across to the right as it's a positive number, and the number underneath is telling us how far we are going up because it is a positive number as well. So 4, 2 as a vector is represented by a straight line with an arrow. Now, a couple of things for your notebook here are the definitions of a scalar and a vector. A scalar is something that has only magnitude. That means it is a number, it has a size. A vector has both magnitude and a direction, and that's why we denote a vector with an arrow. Now, there are a couple of ways that we can write down vectors. Sometimes you'll see them in textbook in bold, but obviously that's very difficult to actually write with handwriting, and so we underline the letter to represent a vector. Let's take a look at these two vectors. So we have 3, -1 and -3, 1. This is the first vector, 3 across and 1 down. And the second vector, 3 across but to the left now and 1 up. These vectors have the same length, they have the same magnitude, but they're going in the opposite direction. So if we were to call this vector A, then the other vector would be -A. Let's take a look at the vector that connects up two coordinates. So here we have the point A, which has coordinates 3, 1, and the point B, which has coordinates 8, -2. Now if I plot A on here, and I think I'm just going to need a scale on here so this makes a little bit more sense. If we call this the y-axis, and this our x-axis here, so x and y. So A is 3 across and 1 up, and B is 8 across and 2 down. And we draw the line that connects these two up. The vector between these two is 5 -3. Let's have a look as we go 5 units across, 5 squares across, 3 squares down. So the vector AB, which can be written as a capital A, capital B with an arrow on the top. Sometimes you might see this like a half arrow, and that would be fine as well. Let's take a look at these three vectors. Here is the vector A, B, and C. Let's have a look at the relationship between those three vectors now. So we have A, B, and C. If we multiply vector A by 2, that would be the same as having vector B. If we multiply vector C by -4, that would also give us the same as vector B. Now you could do this calculation as well, so we can actually multiply a vector by a number, by a scalar. So 2 lots of A would be 2 times 2, which is 4, and 2 times -1, which is -2, so you can see that is B there. And if we did the same thing for C and did -4 lots of C, -4 times by C, that would give us 4 and -2. So indeed it does give us the same thing. Now, because we have this scalar multiple, so we say 2 is the scalar multiple, -4 is the scalar multiple, then all of these vectors are parallel to each other. So if we can find a number, multiply it by both components of a vector to find another vector, then we can say that these are parallel vectors. Let's have a go at drawing these two vectors. So the vector that connects A to B is 3 across 2 up, and the vector that connects A to C is 6 across and 1 up. If we look at the diagram, we can now calculate what the vector that connects up B and C would be. That would give us 3 -1. Now we can also work out this calculation by just looking at the vectors AB, AC. And this would allow us to not have to draw that diagram in the first place. So the vector BC can be found by working out BA plus AC. You may see this written in a slightly different form as well. So it could be written as -AB plus AC. Now I'm giving it in this form because that's what the original form is given within this question. And if we try and draw a path that takes us from B to C, it sort of makes sense that we could then use this notation here. So although we know the vector AB, we're going to start at B, we're going to work backwards along it, which is why we have the negative sign, and then we're going forwards along AC, so we have plus AC at the end. Either of these two notations is perfectly fine. If I just get rid of the writing there, you'll be able to see the actual calculation. So if we put these two vectors side by side, and you'll notice here that actually the same notation of what I've just used. So here this is minus AB because we've got a negative sign outside. Remember that BA, the vector BA is the same as minus AB, so that's an important one to think about. And if we add together the components, so the first two components, the first two elements of that vector, that would give us 3. And if we add the second two, that would give us minus 1, which is the same as looking at the diagram above. Just be careful here, that minus on the outside means we have multiplied that vector by minus 1, so we've taken that sign in. So that top number would be minus 3, then plus 6, that's why we've got the 3 here. And minus 2 plus 1 gives us minus 1 at the bottom. So in your note, we have a little bit of notation. So when we are looking at the vector BC, this is called the resultant vector. Let's take a look at this example. We're told a little bit of information. So we are given the vectors A, B and C. And these represent the vector between the capital letters AB, capital letters BC, capital letters CD. We're also given a little bit of extra information here at the top, so that EF is equal to BC, AF is equal to CD, and GD is equal to 2 lots of AB. So you might like to draw that onto your diagram as well at this point, so we can add a little bit of extra information on. So BC and EF are the same, so I'll write B on here. AF is equal to CD, so I'll write that on here. And GD is equal to 2 lots of AB, so we can write 2 lots of vector A. Now this is also a common thing as well, so where we have AB and A, these are equivalent to each other. AB is telling us, the one on the left here is telling us that we are connecting up 2 points A to B, and the vector in between, so that's the notation of the actual line itself that we would denote with the A with the underscore. Now if we take a look at the first example, then you can have a go at the others yourself. So if we look at AD, how can we work out a path that takes us from A to D? Now the direct route is clearly along this straight line here, but we don't know this length, so we have to combine the vectors that we do know. So the only way around this is to use vector A plus vector B plus vector C. So AD can be written as A plus B plus C. Pause the PowerPoint now, have a go at answering the other questions here for the other vectors, and then we'll take a look at the answers to these. Okay, so I'll just get rid of the extra notation on there. Let's take a look at AE. So A to E, we're going along this line down here. How can we get there? Using the information that we have on this diagram. A to E, we can use vector C and vector B. Now, if you notice this, one thing I haven't written on this diagram is the direction here. So when you are going along this first vector, it's in this direction, and this vector from E to F would be B. So we have to travel backwards along EF, and that's why we have minus B in this section here. Looking at the next one. So F to D, we are looking at travelling along this line here. I'll just make sure that I pop these back on. So that was C and that was B, just in case we need that. So in order for us to travel along F and get to D, we would need to use the vectors that we already know. So you can see C's on here, so I'm going to travel backwards along C, forwards along A, forwards along B, and forwards along C. And because I'm travelling backwards along C and then forwards along C, they would cancel out, and that would leave us with just A plus B. F to G. So F to G now, we are travelling down here. Just rub out these extra lines. So travelling along F to G. And I can go along here, here, and it seems like a really long route, but things do start to simplify as you go along. So we have backwards along C, forwards along A, B and C, and then this vector here, make sure we put the correct direction on. So this is two lots of A in this direction, so we're going backwards along the vector GD, so that would be minus 2A. Now when that's simplified, that simplifies to B minus A, but if you write everything out first of all, that would give you minus C plus A plus B plus C minus 2A, and hopefully you can see that that does indeed simplify to B minus A. Okay, let's have a look at that last one. So E to G. E to G is down here. How can we go along E to G? Now, there's a couple of things that we could do here. We do know A to D. I can write that on here. That's A plus B plus C. So we can use that as well. I think I might do that this time. You don't have to. You could go all the way around and use different ones, lots of different variations, but you would end up with the same path. So E to G, we know B, this backwards along C, forwards along here, and then backwards along this one. And if I write that down, that would give us B minus C plus A plus B plus C minus 2A, and then that would simplify to 2B minus A. Sometimes you'll be given a problem such as this one, where you're given some information, a diagram, and the way in which you have certain lengths of a diagram that are related to each other, connected to each other, and you have to be able to solve this problem. Now, there's quite a lot of working out that's involved with this, but it does take just a reasonable amount of logic as you apply each of the rules for vectors as you're working through. So if you take your time, you shouldn't have any issue with this. If you need to go back through, just rewind the PowerPoint and go through this again, just to maybe explain all of the steps. So just a couple of things to point out just before we get started on this problem. OP has a length of A and OB has a length of B. Now, looking at the information that is given on the right hand side, we're asked to find the value of lambda. Now, that is a Greek letter and it's just going to note a multiple, it's going to note a number. And where does that number come from? So if we take a look at the information, we have the vector OA is equal to 3 lots of OP. So that means that OA must be equal to 3A. And BX is equal to some number, some multiple of BP. And that's the thing that we're trying to work out. So we're trying to work out what lambda must be. A little bit of extra information. M is the midpoint of AB, so it's the halfway along. And XM is parallel 2OB. So let's take a look at how we deal with that very last line there. If XM is parallel to OB, then it must be equal to some multiple of B. Now I've called this mu, and that is another Greek letter mu. If you're writing it, just write it with a stick down, and then it looks like a U after that. Let's build up this problem then. So we're going to start by having a look at the vector AB. How do we go from from point A to point B using the information that we have? Now we know that this full length vector here is 3A, and therefore the vector AB must be B minus 3A. Now you might write that as minus 3A plus B, but that would be exactly the same thing. And it's always better to put your negatives at the back so that you don't confuse them as you're working through. Looking at BM. BM is half of AB because M is the midpoint of AB. So the next thing that we can write down is the vector BM. Now just be careful with this because BM is in the opposite direction. So it is half of the vector BA. And so you need to be careful with your negatives as you go through this. So if AB is B minus 3A, then BA is the negative of that, so multiply everything by minus 1. So you can see that the letters have switched position and switched sign there, and that's why. If we look at the vector BP, so we're going from here now to here, we have enough information to get us from B to P because we can travel from B to O and then from O to P. So that gives us this vector. I'll just rub that extra information there. There we go. So the vector BP is A minus B, or you might have written minus BA, and that would be the same thing. And then the next step is to have a look at BX. So this is what we're trying to get towards, and this is why we've built up this problem to try and get to this here. So we need to know what BX is. Well, BX is some multiple of BP. So I've substituted where you've got BP in this equation, I've substituted it in, and we now have lambda lots of A minus B. So we're trying to solve this problem and work out the value of lambda. So let's take a look at another way of looking at this, and then we'll piece everything together. So looking at the vector BX, we can work out BX by going along BM and then adding MX. So we're going across this vector and then along here. So this will tell us what BX is equal to. Now we know what BX is equal to already, so we can start to substitute in the things that we know. We know what BM is equal to. We found that earlier as well. And MX is given up here, or XM is at least, and then we just need the negative of that if we're looking for MX. So if we substitute those things in here, so I'll just highlight those where they've come from. So looking at BX, that has come from here, and then BM is this expression, and then MX is the negative of this here. Now if we multiply everything out of the brackets in this equation, so the left hand side and the right hand side, this is what we will be left with. And from here we can start to solve this question. So let's take a look at where those numbers come from. I'm just going to remove a bit of writing at the top so I've got a bit of space. So looking at that bottom line, if I look at the coefficients of A here and here, I have lambda A is equal to 3 over 2A, This is the reason why we have lambda is equal to 3 over 2. And we don't even need to have a look at the other part of this unless the question was asking us to work out the value of mu as well. If that was the case, we could then substitute our value of lambda in and solve that equation to work out what mu would be. Now, using vectors to prove the points A, B and C all lie on a straight line. Let's see how we would go about doing this. So when we're looking at coordinates, they're all taking their position from the origin. So the on our diagram is the origin here. And we can work out the vector AB. Vector AB is 2 minus 1. We can work out the vector AC, that is 6 minus 3. How can we prove that these 3 points lie on the same line? Well, the vectors AB and AC are multiples of each other and therefore they are parallel to each other. The vectors AB and AC also share a common point. They share A in this case. And that is all we need for the proof. So we need both this piece of information and this piece of information in order for us to complete our proof. So we are showing one, they are parallel to each other. Now that's not enough for the proof, because if you have this line and this line, they would be parallel to each other, but they wouldn't be on the straight line. Now that you've shown that there is a common point, there is only one possibility, and that is that they are on the same line. So for your notebooks now, the vector that starts from the origin is called a position vector. If we have the vector xy, we can write this in terms of the origin by looking at the vector that would take us from the origin to the endpoint x, and the vector that takes us from the origin to the other endpoint of our original vector y. Now xy can be written as the vector xo plus oy, but more commonly you will see this written in this form. So xy is equal to oy minus ox. That's much more common to see it in that form than it is this one. If 3 or more points lie on the same straight line, they are called collinear. Here we have 3 points, x, y and z, and we need to do something similar to what we just looked at moments ago. If we're going to prove that these lie on a straight line, there's a couple of things we need to do. First of all, we need to work out the resultant vectors between 2 pairs of points. So we could take the vector xy and the vector xz, xy and xz. Or we could take the vector xy and we could find the vector yz. Either of these 2 different possibilities would lead to us proving the same thing. If the resultant vectors are multiples, then that is telling us that they are parallel to each other. So that's the first thing that we would have to do. And the second part of this proof is to show that they are sharing a point. Now that's fairly obvious, because if you're taking these first 2 points here, they are going to have x and x. So it's a little bit trivial, but you do have to point this out because this is part of a proof. And as long as you have shown that they have a common point and you have shown that they are multiple, so they are parallel, that is enough to show they are collinear. But you have to do both of these things in order to do that. Please turn to pages 122 and 123 and complete exercises 1.2 and 1.3. Taking the general column vector R, which is denoted by AB, where A and B are represented by the amount travelled horizontally and B by the amount travelled vertically. So A would have a vector A0 and B has a vector 0b. The first piece of terminology we need is what a unit vector is. So a unit vector is a vector that has a magnitude of 1, so a length of 1. Now if we look at a unit vector, that would be denoted by 1, 0. That vector has a length of 1. If you started at the origin, plotted the point 1, 0 and measured it, that would be 1 unit. And this is denoted by the letter I. The unit vector 0, 1 is called j. Now if you're looking on a coordinate grid, so where you have your x and y axis, then I is represented by this vector here and j by this vector here. Now this I has a length of 1 and j also has a length of 1, and we can use this to denote our original column vector r in a different way in terms of i's and j's. So we can say r can be written in this form as a column vector, or it can be written in this form where it tells us how far to go across the x direction and how far to go across in the j direction. If we look at the magnitude, the length of a vector, that is written as this symbol here where we have the vector in between these two straight lines. This is called the magnitude. Sometimes it's called the modulus of r, mod r. So just be aware that the terminology means the same thing. And whenever you see this, you are just looking at the length of this vector. Now the length of this vector can be found out by using Pythagoras theorem. So we are working out the square root of a squared plus b squared. That gives us the length of r. Now the direction of a vector is measured from the positive x-axis. If you imagine that we have a set of axes going across and up here, so this is our x-axis and this is our y-axis. This is really important for vectors. When you're measuring the direction of a vector, it is normally measured anti-clockwise from the positive x-axis. So you can see the theta in this diagram. It's been turned anti-clockwise, but from that positive 0, the origin, and the x-axis. So we can represent a vector in a different form. We can represent it in the column form, or we can represent it using this magnitude and this direction. Now if we wanted to work out theta, we would have to use a little bit of trigonometry here. You do need to be careful, and I'd always recommend a sketch of a diagram, because if a and b are not positive, then you need to consider something else here as well. So the diagram is always useful. So if a and b are both positive, then the direction of the vector r is calculated using this formula. So the inverse tan of b over a, and that would be, using trigonometry, it would be the opposite over the adjacent. Okay, so looking at these vectors then, if we are looking at the first one, vector A, that is 5i plus 3j. Now remember that this could have been written as 5, 3 as a vector. So here we have the vector A. If we want to write down its magnitude and its direction, its magnitude is root 34. Where does this come from? That's the square root of 5 squared plus 3 squared. So the square root of 25 plus 9, which is the square root of 34. If we then want to work out its direction, we are trying to work out this angle here. And where has this come from? This has come from the inverse tan of the opposite, which would be 3, divided by the adjacent, which is 5. Okay, just get rid of my annotations on here. Looking at vector B, so now we have minus 2i plus 4j. The magnitude, nice and easy to work out again. So this again is using Pythagoras theorem. So we would have the square root of minus 2 squared, so that's 4, plus 4 squared, which is 16, and then we've just simplified it using the rules for seds to 2 root 5. Your calculator will handle this nicely. The second one here is the magnitude of this vector. Now, in order for us to calculate this, we are not going to use that positive x-axis. We're going to form a right angle triangle here. We're still going to use the same formula, but our answer overall, we just need a little bit more thought and care, and this is why you need to draw a sketch for each of these diagrams before you begin. So if we were to work out theta, theta here is 63.4. Now that comes from the inverse tan of the opposite of the adjacent. Now the opposite is this length here, that's 4. The adjacent is 2, so 4 over 2. This will give us the 63.4 indicated on the diagram, but that is not the magnitude of this vector. The magnitude of this vector is given by the angle made with the positive x-axis travelling round anti-clockwise to the vector. So we use this trigonometry here in order to work out this angle, and then we just need to work out the actual magnitude by taking this number 63.4 away from 180 degrees, because that's a straight line going across here. So we have 180 subtract 63.4, and that gives us 116.6. Now I'm just going to get rid of the annotations on this diagram at this point. Pause the PowerPoint now and have a go with the following two vectors, so C and D. See if you can come up with the correct magnitude and the correct direction. So here is C, minus 3, minus 3. Its magnitude is 3 root 2. So that would be the square root of 3 squared plus 3 squared, so the square root of 18. And that simplifies to 3 root 2. The angle now, so the angle made with the x-axis there is 45 degrees, and that would be the inverse tan. So inverse tan of 3 divided by 3, because that is what the triangle would be here. That would give us 45 degrees. Now we need to measure anti-clockwise from the positive x-axis, so that is this great big arc going all the way around. So we are adding on 180, this angle here, onto 45, that gives us 225 degrees. The final one. So looking at part D, so here we have vector 5 minus 4. The length of this is the square root of 41. That comes from 5 squared plus 4 squared. And then our angle this time is 38.7. Where has that come from? Well, we have a length of 4 and 5 on this right angle triangle. So we have the inverse tan of the opposite over the adjacent, and that gives us 38.7. We need this angle going all the way around from the positive x-axis, travelling anti-clockwise. That's 360 subtract 38.7, which is 321.4. So what you should take from this, the most important thing, whenever you're trying to work out the magnitude and the direction of a vector, always sketch first. Do not try and learn the rule. Try and make sure that you sketch the diagram and then have a think about what the direction should be before you write anything down. Now there are a couple of ways that you can write down the direction of a vector, so you might like to put this in your notebook. So this is just a way to remember exactly what you need to do, the rules around this. You don't need to learn this, because if you draw a sketch, then it should be quite easy, common sense as to what the angle should be. But if you'd just like to have something to look back at, then this is a good table to copy down. Okay, so this is another example for your notebook. This example is including bearings. Now, bearings have a slightly different notation, so just be aware of bearings are being measured from the north line. Let's take a look at this now. So ship has an initial position that is on a bearing of 125 degrees and a distance of 25 miles. Sketch the ship's initial position and work out its position vector in its component form. So a bearing starts from the north line and it always goes around clockwise. So if a question is saying anything about bearings, please do bear in mind these couple of points here. Now if we're going to sketch this, we have an angle of 125 degrees. This is our rough sketch to begin with. And here we have a vector that is representing a distance of 25 miles. So S is the position of that ship. If we're going to calculate this in its component form, that means in the I and J form, so this is us working backwards now, going from an angle and a length into its actual vector form. Now, hopefully you can see that if that is 125 degrees from the north line, then if we're just looking at the triangle that is formed below the positive x-axis, this angle that we're interested in, so that we can use trigonometry, is 35 degrees. So we've subtracted 90 degrees, this angle here, from 125. And then from here we use trigonometry to work out the lengths of A and B. So we have, this would be from, I'll write it down here, cosine is equal to the adjacent over the hypotenuse. And we can rearrange that. So if we multiply cos 35 by 25, and do be careful when you type this into your calculator that if there is a bracket that you make sure that that is closed, otherwise your calculator may make a mistake there. And the second one is sine, and the sine is equal to the opposite over the hypotenuse, and we can rearrange that to work out B. Now it's important that when you look at this calculation, it will give you 14.3 as the size, as the length of that line, but it doesn't give you the direction. And this is why the sketch is again really important, because you are going down with this vector, and so the number in your vector should be represented by minus 14.3. So the position vector of the ship is 20.5 minus 14.3, and that can also be shown in its I and J. Please turn to pages 124, 125 and 127 and complete the exercises shown. For this final example, and please do copy this down into your notebook as well, we're going to work out the angle AOB, and we are given the vectors OA and OB. So let's draw these on. So this is the position vector OA, the position vector of OB, and we want to work out the angle between them, the angle enclosed, and that's why we have this little hat symbol on top of the AOB here. In order to do this, we need to work out the lengths of OA and OB, and then we need to connect A to B and work out its length as well. In order to work out the side lengths, we use Pythagoras theorem. So the square root of 52 there comes from the square root of 6 squared plus 4 squared. That's from the vector OA. And OB has a length of the square root of 34, and that comes from 5 squared plus 3 squared, and that's Pythagoras theorem on the vector OB. If we connect A to B and we calculate this using this rule here, so OB minus OA, that gives us a vector of minus 1 minus 7, and so the length of AB is the square root of 50, and that has come from 1 squared plus 7 squared. We can then use the cosine rule to work out the angle of theta. So here is the cosine rule. Now the only thing that you have to bear in mind here is which is A, which is B, and which is C. So the A here has to be this length opposite the angle. So do bear that in mind. The B and the C can be either way around, but the A has to be the opposite of the angle there. So just be careful as you type this in or enter that into your function in your calculator. This will then give you an angle of 64.7 degrees. Please turn to pages 128 and 131 and complete the exercises shown.